So there's a quiz coming up on a week from today, or an exam rather, an exam. And there's some practice problems here on this web page. And we also need to move forward and look at functions, and maybe spend some more time with algorithms as well, some of those issues in there. But so I want to, if there's anyone that has some pressing question, or just a question or a problem that you want to look at now, then to mention that, and I'll talk about it. So is there anybody that wants to look at a particular lab exercise, or wants to focus on the practice exam problems? What do you want? What is the feeling back there? Nothing? Practice exam problems?
Yeah, that's one.
Now, if you look here, I've got these problems from an old exam, and then I have the answers, and then I tacked on lots of answers here. Then at the bottom, I've got some more problems, but I don't have answers for these. So what we could do is maybe go through some of these, take a look at these that don't have posted answers. Let's take a look at the first one. So when this code runs, what does it print to the console? And let's see, I'm going to, let me call this exam 1. And this is additional problem 1. So when this code runs, it's got a loop in there. And the printing operation is inside the loop. So we're going to be repeating something. We're going to print something probably more than once. And that's different than this problem here, where the printing operation is outside of the loop. So we'll only print one number in that case. So basically, you just have to keep track of the variables and see how they change. There's only one variable in this problem, I. And we set I initially equal to 1. And then we enter into this while loop, which is, remember, a while loop is dependent on this thing called the loop condition. As long as the loop condition is true, we're going to repeat the statements. We're going to execute the statements in the body of the while loop. That's the lines of code that are in between the opening bracket and the closing bracket. And notice also how I indent these two lines. Those two lines are indented just visually. It's not needed by the compiler, it's needed by the human to visually see that these two statements are substatements. They are statements within the while loop. The while loop is a single statement itself, but it's comprised of substatements. So this is one statement. We execute the statement and we move on to the next statement. But executing this statement is not so simple because it involves repeating substatements as long as the loop condition is true. So the loop condition, when we first arrive at this while statement and we run it, and we look at the loop condition right off the bat, and the loop condition is true, and so we carry out these commands here. Now let's look at it. So I is initially 1. What do we print? Well, there's got an I plus 1 in there. Do we print 1 or do we print 2? We print 2 because this operation is done before the output operation. So I plus 1 is computed. And then that evaluates to 2. What I've highlighted evaluates to 2, and that gets printed. So we print a 2. And then we print a blank. I just put that in there just to, so the output would be easier to read. Now, after this statement completes, what does I equal? What does I equal after that statement completes for the first time? This is a very important thing to know, to understand. You can't solve these problems until you get this. What does I equal? Did I change in this statement that I showed you? I was not modified. There's no assignment to I. There's no changing of what I is. There's only using I. We're using I. We're adding 1 to I. The result is 2, and the 2 is sent into Cout. I is not modified. So I remains 1. Okay, that's the first thing. Everyone should be absolutely clear about that, because in the beginning of this course, a lot of students that are confused about that point. For I to change, there has to be some kind of an assignment operation. There's no assignment operation here. In the next line, we have an assignment. Do you see that? That's an assignment operation. That's modifying I. The left-hand side is I. The expression on the right-hand side is evaluated, and the result is assigned into I. Now, I is 1. And so 2 times 1 is 2. And that's the result of this expression. This expression evaluates to 2. And that 2 is now assigned into I. So I becomes 2. I'm just going to keep track of what I is up here. I was 1. I was 1, but now it's 2. And that's the end of the loop. That's the end of the body of the loop. Those are the substatements. They've been executed. So the next thing we do is evaluate the loop condition. And we're going to keep doing this until the loop condition is false. When the loop condition becomes false, then the while loop is finished. And then we go to the next statement. And I mean the next statement. This is the second statement. This is the third statement. And there is, in our code, there is no third statement. So it means we're done. These are not part of the main flow. These are substatements that are repeated. So you can think of them as, as second level statements. Those are, when the while loop is finished, we move on past the while loop. All right, anyway, coming back to the loop condition, 2 is less than 128. We made a record of what I is. It started at 1, and then we doubled it. Now it's 2. And 2 is less than 128. So we do this again. We take what I is and add 1 to it. So it's 2 plus 1, that's 3. So this statement evaluates, this expression here evaluates to 3, and we print 3. 3 is sent into Cout. And then after we send 3 into Cout, what I have highlighted right there evaluates to Cout. Is that weird? So when I say I plus 1 evaluates to 3, so you can think of taking I plus 1 and replacing it by a 3. And then that 3 is sent into Cout with that output operator. And then this expression that I have highlighted evaluates to Cout. That means you take what I've highlighted here and just replace it with Cout. And that's why this makes sense, because the left-hand side of that second output operator is Cout. As a result of the first output operation is Cout. That lets us chain these output operations. And this is a very common sort of syntax and pattern that you see in computer languages. You can do this. You can chain these expressions one after another. You chain these operations. So anyway, we print the 3. I is not modified. We're going to modify I in the next line. So is I, so we've got to go 2 times I. Is I 2 or is I 3? This is where I'm just going slowly here because every quarter, half the class gets this wrong. There's 2. We didn't modify I yet. We printed 3, and that doesn't make I 3. That just means we printed 3. All right. So 2 times 2 is 4. I'll assign that into I. So I becomes 4. See, I'm keeping a record there, just so that I can not worry about forgetting what I is at a particular time. We go back to the loop condition. I is less than 128. That's true. We print I plus 1, so we're going to print 5. Then we're going to double I, so I becomes 8. See, now we got the pattern figured out here. 8 is less than 128. We're going to print I plus 1, that's 9. We're going to double I gets to 16. We're going to print I plus 1, that's 17. And we're going to do that. It's just going to keep going up, right, to 64. And then I will eventually hit 128. Now, when I is 16, we're going to print 17. When I is 32, we're going to print 32. When I is 64, we're going to print 65. Now, when I becomes 128, which it does here, this is where I is modified. I was 64. Now I is doubled. I becomes 128. Do we print 129? No, because we've got to evaluate the loop condition, which is now false. The loop condition is false, so we're finished. Okay? All right, I'm going pretty slowly on that one. I suppose k is an integer variable. Write code that prints good when k is either positive or equal to -1, and bad otherwise. Yeah, it's a little hard to understand, right? Yeah, let's stretch it like this. Write code that prints good when k is either positive or equal to -1 and bad otherwise. So we can just use k. I say suppose k is an integer variable. We don't have to declare it. I didn't say declare k as an integer variable. Just suppose k is an integer variable. So we have a condition. If something, then print bad. I'm sorry, print good. And else print bad. So what we need to do is figure out that expression there. When k is either positive or -1. So if k is positive. If k is positive, in other words, if it's greater than 0, that's how to say k is positive. If k is positive or equal to -1, or equal to -1. So but that's not quite how we do it. So we have to duplicate. We have to say if k is positive or k equals -1. We need to repeat the variable there. And or, this language doesn't take the word or. Some languages do. This one doesn't. We use this symbol here, this double vertical bar. If k is greater than 0, if k is positive, or k equals -1, then we print good, otherwise we print bad. When the code in figure 2 runs, what does it print? Let's take a look at this. So once again, we glanced at this a moment ago, and we noticed that there's only one output operation, and it's done after the loop. So we're only going to print one number. So what is that one number?
9.
What is n going to be? This one is, it looks like it might be more difficult than the other one because there's 2 variables. But actually it's not, because k is set to 901 here. And it is never modified. K is never modified. There's no assignment operation that modifies k. And so this k here in the loop is a constant. It's always 901. So you can mentally replace k with 901, and you're okay. So the only variable that changes is n. That's the one we have to keep track of. And that assignment to n is done here. Oh, there's another variable that changes. It's I. And this is where I changes. That's an assignment operation there. I don't know if we can call it assignment. I think you can call that an assignment operation. So I is changing and n is changing. I just gets incremented by 1 in the loop. Every time we run the loop, I is incremented at the bottom of the loop. This part of the loop, which is following that semicolon at the very end, that's the operation that's done at the end of the loop. The first section, this is the operation that's done when you first enter the loop. It's only done once. So we usually declare a variable and initialize it. Here we're declaring I, initializing it to 0. And then we have the loop the loop condition, like in the while loop. So I needs to be less than k. Once again, k is 901. It never changes. So while I is less than 901, we do this. So how many times does the loop run? 901 times. This statement executes 901 times. Now, how do we know that? Yeah, see, this is true. Or I starts at 0. So we do it for I equals 0. We do it for I equals 1. We do it for I equals 2. We do it for I equals 900, right? But as soon as I hits 901, the loop condition is false. So we do not run this statement when I becomes 901. We only run the statement when I is 0, 1, 2, all the way up to 900. Well, how many states of I are there from 0 to 900? 901. Remember, we're starting from 0. We're not starting from 1. We're not saying 1, 2, 3 to 900. We're doing 0, 1, 2, 3. So it's 901. And, we could have written that differently. We could have said I less than or equal to k equals 900. We would get, and then start I equals 1. We could reorganize the code to make it more like the way a human thinks. But it's just not what you read when you read computer code. When you read code written by other people, this is the style that's used. Of course, when you go deeper and go to the hardware level, you'll see that this is how the hardware works. I mean, the hardware starts counting at 0. That's it. So it makes it easier to work at lower levels when you adjust your thinking and your coding style to match the way the hardware works. And this is the typical expression. So normally you'll see a loop written like that. So you have to get used to it. So anyway, this line here that I have highlighted runs 901 times. So we're going to add 1 to I 901 times. We're going to add 901 ones. That's adding 901 to n, isn't it? So n started at 0, and we added 901 ones. We added 901. So n becomes 901. So we print 901. Now, if you're not sure about that, then you should, after you go through that thinking process, that mental walkthrough, then you should code it up and then run it and see what happens. What about this one here? I talked about this a little bit. This is a post-increment, and this is a pre-increment. They both increment n, but they perform the increment at different times. The simple one is the pre-increment. That's the one where when you see the pre-increment operation, pre means the operator comes before the variable. Post means the operator comes after the variable that it operates on. So when you see the pre-increment operation, and you can have pre-decrement too, so you can have minus minus also, by the way. So when you see this, you just do it immediately. Just increment n right away. And that's it. This is the first thing you do. It has very high precedence. But the post-increment is that means, oh, let's use n first. Let's read n. Let's use its state in the expression within it, which in it appears. And then after you use the value of n, after it's done being used, then increment it. So it's like a delayed increment. So let's see here. Let's keep track of those two variables. There's n, which we initialize to -1. And there's k, which I don't know yet. We got to think about that. So here we declare n, initialize it to -1, and I made a record of it right there. Now we're going to declare k and initialize it to the result of this expression. All right, well, let's figure out what that expression evaluates to. Well, once again, this is the post operator, so we don't increment n until we use it within the expression in which it appears first. So n is -1. We're not going to increment it. We're going to delay that. N is -1. So -1 times 2 is -2. And -2 is then assigned to k. So k becomes -2. Are we done? No, we're not done. Now we increment n. N. So then we got to increment n, and -1 plus 1 is 0. Now we're done. So you can think of a statement like this as really having two phases. The first phase is to actually run the statement itself without executing the post increment. And then once that's done and all the consequences are resolved, then you can perform the post increment. It's as if you inserted another statement right after it that incremented n. That's what you could have done. We could have, I'll show you what this line here, it could have been written as follows. We could initialize k and set it equal to n times 2, and then increment n. These two lines are identical to that line. Let's suppose we did this. That means we increment n first, and then perform the rest. So this statement is equivalent to these two lines. It's just the order in which, where you increment the n. All right, so we have one more line to do, and that's this one here. And so we've got to stare at that and we say, well, what do we do first? Well, we've got parentheses, and that parentheses always help us know what to look at next. So that modulo operation, mod 4, that's going to be at the end. We have to evaluate what's in the parentheses first. Inside the parentheses, we've got an addition and a multiplication and a pre-increment. Now pre-increment, let's take care of that right away. That's a pre-increment. So I'm going to increment n. N becomes 1 right off the bat. So now we can ignore that increment. I've got n times 16 plus k. Well, n times 16 has got to run first because multiplication has higher precedence than addition. So n is 1, n times 16 is 16, and we take 16, we add k. K is minus 2, so this expression is 14. This becomes 14. So now what we want to figure out is what is 14 mod 4. What's 14 mod 4? So we take 14, divide by 4, what's the remainder? 2, good. So it's that's going to be 2. Sorry, that should be equal there. So 2. And we don't need this. That's the answer to the problem, 2. So, you know, the purpose of these exercises is for you to learn how to read code, how to walk through it mentally, how to understand how the operations are being performed. That's the main purpose of exam 1, is learning how to read code. Shall we keep going on this, or we're okay? All right. All right, number 4. No, I'm sorry, number 5 we're on, right? So 5 refers to figure 4. So when the code runs, what does it output to the console? Here it is right here. What does this do? That's going to be number 5. So I'm just going to go up like that. All right. Well, once again, we only have one variable I. So maybe we're going to keep track of that. It's initialized to -1. Then we have a loop, and when the loop finishes, then we print I. So there's 3 statements, 3 top-level statements. And there's one statement that's a substatement of the while loop, one statement that's a substatement of the second statement. So while I is less than or equal to 999, we're going to add 200 to I. So I starts at -1, and as long as I is less than or equal to 999, we're going to add 200 to I. So the first time we execute, when we just enter the loop condition is true, because -1 is less than 999, so we add 200. So I becomes 199. And you see that's I is less than 999, so we keep adding 200. So we just keep adding 200. So this would be 399, and then 599, and then 799, right? Let's go slow because we're getting close to 999. So when I is 799, the loop condition is true. We add 200, so we get 999. So when we finish this assignment, we get 999. The loop condition is true, so we add 200, which is, I got to figure that out, 1099, 1199. That was the hardest part of the problem right there, is adding 200 to 999. Did I get that right? Yeah. Yes. So, and that's what we print. So when I becomes 1199, the loop condition is false. All right. What about this one? When this code, number 6, rather. there's number 6 is this code here. So we've got two variables, I and j, and another variable, x, which is a double. I and j are integers. X is a double. And you can see there's division here. So remember, there's two kinds of division. There's integer division, which lops off any fractional component that's resulted from the division. And then floating point division, which retains the fractional component of the division operation. So I divided by j, is that integer division or floating point division? Integer division, because I and j are both integers. So the compiler says, oh, in this context, that's integer division. So I divided by j is 1 divided by 2, which is, everybody know? 0. Okay. 1 divided by 2 is 0. Because there's no fractional part, and we're not rounding. To round, you have to add 0.5. So 0 greater than 0, that's false. 0 is not greater than 0, so we do not print alpha. What about x divided by j? Well, x is 1, and it's a floating point value, and j is 2, and it's an integer value. So the result is that integer division or floating point division? It's floating point division. And the result will be a half, a floating point number. Compare a half to 0. A half is bigger than 0, so that's true. So we're going to print beta. All right, what about this one? Figure 6. What does figure 6 do? We assign 2 to I, and then we go into this loop. So we have the loop. Obviously, I is not the loop index. I is not the counter that we use to control the loop. We're using the variable k here. So initialize k to 0 inside this loop. K starts at 0. While k is less than 500, do the loop. And then at the end of the loop, we increment k. So we're using k instead of I there. And I is being modified here. So this looks like the other problem we did. So k is never modified. K is modified here. So we can see that that the loop runs exactly how many times? 500 times. So you should be getting that pattern by now. Right? This is the standard expression. Assign the index to 0, and then while index is less than the number of times it's going to run the body of the loop. So this runs 500 times. So we add 500 2's to I. We add 1,000 to I. So I becomes 1,002. Everybody see that? We're going to add, the loop runs 500 times exactly. Now on the exam, you have to get this exactly. If you think the loop runs 499 times, you're going to get a 0 in this problem. You have to calculate this exactly. So practice getting these answers exactly. There's no partial credit to getting a close value in these problems. All right, write code that computes the sum of integers 100 through n inclusive. This is a typical problem. We have to add the numbers 100 plus 101 plus 102 all the way up to n, whatever that is. N is some number strictly greater than 100, but we don't know what it is. It's a variable. So we have to perform something repetitively. We have to perform this addition repetitively. And we have to do, we basically have to compute this. That's what we need to compute. So we don't want to modify n, we need to keep track of n. So we need another variable that is used to iterate through these values. The other variable will first be 100, then it'll be 101, then it'll be 102, until it reaches n. So we need a second variable. So I'll show you one way to do it. So let's use k, say. Well, let's use I. So we'll start with I equal to 100. And then we're going to repeat as long as I is less than or equal to n. We're going to repeat an operation. We need to compute the sum, right? So this is going to be some value. And so, we need another variable to keep track of the values that we're adding together. So first, we'll add in 100, then we add in 101 and 102 like that. So we need another variable, and I'll call it sum. I'll initialize it to 0. And in this loop, we're simply going to add I into sum. So this operation of taking the value I and adding it into sum, it will be repeated for I equal 100, 101, 102, all the way up to and including n. Of course, sum is our answer here. So I didn't ask for this. Oh, whoops. We could have done something like this at the end. We don't have to I would have been happy without this last line because I didn't ask for it here. But, sum is the result of that calculation. Now this is, another way to do it is to use a for loop. We initialize I to 100. And while I is less than or equal to n, increment I. So that's the way to do that with a for loop. It's more compact. But both are acceptable solutions. Whichever one is more readable to you is the one that you should use. Or the one that's more readable to me. That's even better. And when you get a job, the one that's more readable to your boss or your client, that's the best solution, isn't it? Or the line that's more readable to the programmers that are going to be maintaining the source code that you write. All right, so two different solutions there. Just pick the one you want. How about this one? Write code that prints every odd number between 100 and 1,000. There's many ways of doing that. Oops. So I is between 100 and 1,000. Is that inclusive? It doesn't say, does it? Well, it doesn't matter because 100 and 1,000 are even numbers, so we don't need to include them anyway. How do we decide if I is odd? Well, if I mod 2 is 1, here's another way to do it. Here's solution 1. Here's solution 2. Initialize I to 101. That's the first odd number greater than or equal to 100. And while I is less than or equal to 999, we'll print I, and then add 2 to I to get the next odd number. There's another way to do it. Those two solutions look very different. Whichever one is works better for you, use that one. Well, maybe I'll leave that open there. How about the last one? Write code that prints 100 random integers, where each integer is between 0 and 99. So we have to print 100 random integers. We have to print 100 something. We have to do something 100 times. We need a loop that runs exactly 100 times. What's a loop that runs exactly 100 times? Well, just use our for loop there. You know, I've got that memorized, so that's easy for me to type out. That's a loop that runs exactly 100 times. Now we're going to do something. We're going to do something 100 times exactly. So we put it inside of that structure there. That's how you repeat something exactly 100 times. So what is it that we want to do 100 times? We want to print a random integer between 0 and 99. Well, let's just print a random number. So we use the rand function here. It suggests that. Use the rand function. And then use the modulo operator to restrict it to 0 to 99. So rand returns a positive integer between 0 and a maximum positive integer. So that's we want the range to be between 0 and 99. So the standard trick is to divide by 100 and take the remainder. That's the modulo operation. So you don't divide by 99 because you'll never get 99. We want 99 in there. We want 0 being printed sometimes. We want 99 being printed sometimes. If you divide by 99, the biggest remainder you get is 98. So you have to divide by 100, and the largest remainder you'll get is 99. That's what we want. All right, that's it for the quiz, or it's for the exam. You really got to practice these. You know, I tried to give as many of these problems as I could for you to practice on. And if these aren't enough, you can always invent some for yourself, of course. Now, these are not that tough. If you practice enough, you shouldn't have any trouble getting a perfect score on your paper. But you have to be careful. You know, a lot of students, they don't, first of all, they don't study enough, and then when they're in the exam, they don't review their work. They just quickly do something and they use their intuition, and that's enough. You know, this is like grinding work. It's you really got to dig down and look at the fine details and force your mind to focus on those fine details and carry out the reasoning process that I'm illustrating to you in these lectures. It's just a habit of mind. You have to practice it. It's like lifting weights, you know, or running. You build up those muscles, and then it becomes easy. I mean, this is effortless for me. It's like breathing. And but for you, it's not something that you're used to doing. So you have to work at it. You got to practice it. And this is the building blocks of understanding and writing complex computer systems. You know, this is how you make robots and control factory equipment using programs and doing financial transactions, and you know, all the stuff that's automated these days. You know, when you dig down into it, you'll see a lot of it is controlled by programs, and you have to learn how to write and develop and understand this kind of these type of things, this code. So I do think it's very useful actually to learn this stuff. Just a little side there is several students in recent years that have taken the classes that I've taught. Actually, they work in manufacturing. They work in factories. And their job is requiring them to write programs now. They're not down on the assembly line stamping out parts and operating machines. They're behind a terminal programming a machine, which is essentially a special purpose robot, to do the work for them. So, you know, the old days, you know, the days of my grandfather, you know, you'd have people on the shop floor operating machines. They still have that now too, of course. But more and more things are automated, and they're automated using code. I mean, this is what it does. This is how you write it. It could be a different language, but it's essentially, they're all very similar. And the thinking style and the thinking process is the same across languages. All right, that's my lecture. So we have a few more minutes. Once again, the exam is a week from today. And today was kind of a review for the exam. So at this point, I'd like to move forward, maybe talk about the functions, unless there's something you want to talk about in Lab 3. Nothing? All right. I'm just going to start with this functions. We'll probably end early today. I'm not going to get long-winded on this. Just give you a taste of functions here. And these are the learning objectives for this chapter. You know, I'm following the chapters in the book, by the way, for those who are reading it. Learn how to implement and call functions. Understand what is meant by the term side effect, and so on. Okay, well, let's start with the first one. Let's learn how to implement and call functions. And I'm just going to copy this. Actually, let me just edit that. So let's do this. Let's have a variable called name. That's a string. Sally. And so we set this string to Sally, and then we say, you know, hi, Sally. And then we'll have another string. say Bob. Hi, Bob. You know what? We're going to need this. I better put the end line here. And I'll group these together. See that? Declare the string name, set it to Sally, print hi Sally. I don't want to declare name again, that won't compile. And then let's set name to Bob and say hi Bob. Let's see if that runs. Hi Sally, hi Bob. We didn't use the period, I think it's all right. Now there's some repetition here. This line right there is repeated twice. So if we needed to do this 100 times, that's a lot of repetition. So one way to solve that problem, to simplify the code, is to declare a function, call it greet, and the function takes a string called name, and it just says hi name. Now we can get rid of both of these lines here, and we can call, greet Sally. That's great, isn't it? And greet Bob. So we've got a bit of code here that we need to repeat. So we put it in a function, and we simply call the function with the variable that. So we get a different result each time we call a function because we pass in a different value. This here, this is called the argument list. So this is where we put the information that's being passed into the function. The function is like a black box. We pass something in, it does something inside of itself, and then it produces an output. Actually, here it's a bit of a side effect. We'll talk about that in a minute. So let's see if this in fact works. Hi Sally, hi Bob. This time I'm going to fix it up a little bit. I'll add that period. There we go, just to make it a little cleaner looking. There we go. So that's how you do it. This is how you declare a function as a return value. In this case, it's a void, means it doesn't return anything. But it has what's called a side effect. You call the function, and it prints out a line. Now, the other way to do this is to have it return a string. So this is going to get complicated. So we're going to return, let's see if I can do it like this. Hi. I think I can do that. So if we greet Sally, we're going to print that. So now greet is returning a string, which is hi plus the name tagged onto it. And maybe we'll put a period on there as well. I think I can do this. I better check it. Yeah, that looks good. And let's put the new lines in there. So what have I done here? Well, I changed the function. It's not a void function anymore. It now returns a string. So that data type, the thing that the function returns, the type of data that the function returns is listed first in this syntax that's used to define the function. So the function returns a string. The function name is greet. And the arguments, there's one argument name, and the argument name is name, and its data type is string. And it just, what does the function do? It takes the string hi, appends the name, and appends the period. And that's what it returns. So this is called a return statement. We could do it like this as well. We could do string, I'll do this, result equals. So we create this, this is called string concatenation. We take 3 strings and concatenate them together and store the result in the variable named result. And then we return the result. So when we say return, we're telling the compiler what variable or what constant, what value needs to be set as what the function evaluates to when it runs. So that's called, and this is the data type here. This is the data type of the function. So when you call this function, greet, and you pass in the argument, what I have highlighted there exactly, this evaluates to a string, because that's the return type of the function. The return type of the function means what data type does the function evaluate to when it's evaluated during execution. So greet Sally evaluates to a string. It evaluates to the string that we return inside the body of the function. Now this formulation is different than the last one because this function doesn't have what's called a side effect, and this is understand what is meant by a side effect here. The function is like a black box. We pass something in, which is the name, and we return something out of it, which is the new string that was formed. And then we use the return value in an expression here in the calling code. The calling code uses the return value to do something, to print it. That's different than printing inside the function itself. When we print inside the function itself, it could be thought of as a side effect. Not always. It's not always a bad idea to do that. But in many cases, you want the function just to do a task. Don't print. Don't write to the database. Just take this input, manipulate it, and return an output for me. And then I'll do what I need to do with that. I'm the one that's going to do the printing. So the calling code is the one that does the printing. But the first formulation I had for the program, I think is acceptable, actually. It depends on the overall program architecture to decide whether something is a side effect or not. And I know that's vague to you, and because we haven't been looking at big chunks of code, large programs, so I don't want to belabor that point, and if that's fuzzy to you, then leave it fuzzy for now. But the thing that shouldn't be fuzzy is how to declare a function like this, how to invoke it, using this syntax. We use the parentheses, we pass in the value of the arguments. We could have another argument. Say if we wanted to have k here, say, and we could do something like for I equals 0 to I less than k plus I result plus equals the name. So we're just going to duplicate the name k times. So now when we call it greet Sally, we'll say we want 1 Sally, but here we want 5 Bobs. There it is, 1 Sally, 5 Bobs. You see how it's, now I'm passing in 2 arguments to the function. It's just more information. And arguments are separated by a comma. You can have any number of arguments. You can have 0 arguments. It's okay. And then what we do inside the function is, our business. And the calling code can forget about that business. See, it makes the program easier to read. We could duplicate all of this logic down in here. First of all, we get duplication, which is not a good idea. It's hard to maintain code that relies on identically functioning duplicate sections of code. It's not good. So it eliminates duplication, and it makes the program, the main thread of logic, easier to comprehend. Oh, we're greeting Sally. Actually, it's not a greeting. This is a bad name now. So we'll call it, duplicate. Give it a better name, because greet is no longer expressive of what this function is now doing. I want to duplicate a name k times. Let's check that. And one more thing I'm going to leave you with here. Let's suppose we define the function after main. This is just a detail. This will not compile, because when the compiler analyzes this code sequentially, and when it reaches this point here where it sees the first word duplicate, it's going to say, what's duplicate? I don't know what duplicate is. So it's going to complain. It's going to say, undefined identifier, something like that. Undeclared identifier, duplicate. So rather than moving this chunk of code above main so that we define duplicate first, we're going to do something called declaring duplicate. Or we're going to add what's called a forward declaration. We don't implement it. We don't show the details. We just say, hey, compiler, duplicate is a name. It's the name of a function that returns a string. It takes 2 arguments. The first argument is a string. The second argument is an int. And I'll tell you later how to implement that function. I'll give you the logic for that function later, but just take it for granted, compiler, right now, that that there's such a function. So when it gets to this line, it says, oh, you want me to call the function duplicate, which you didn't define yet, but you told me you were going to do it. So you use this forward declaration, tell the compiler that a function duplicate is in the works. It's out there somewhere. Don't do it now. Do it later. So there's this 2 major steps when you generate the executable. First step is compilation, where you generate these object files. And then the second step is called linking. And that's where references to functions are resolved. And especially references into functions provided by the operating system, so the program can interact with the operating system. That's called linking. I don't want to get into too many details there, but if we commented this out, it's no longer a compilation error, it's now a linking error. I'll show you that. See, it's different. Undefined symbols. And LD. LD is the linker. Here it says, linker command failed, right there. So it's a different kind of error. We said to the compiler, the function exists. When you get to your linking phase, you'll find it. But of course, it wasn't there. Let's define it now. Even though we define it late, it's good enough. See, there it goes. So that's the beginning of functions. And next time when we meet, I'll talk about some of these other ideas. That's it.